Right, this video is on bond enthalpies, and we have already talked about bond enthalpies, so this will be a short discussion. It was back when we did thermochem, but we had yet to learn Lewis structures, and so I think it's important to come back and revisit this idea with our knowledge of Lewis structures. So bond enthalpy is defined as the enthalpy change for the breaking of a bond into technically 1 mole of gaseous substance. So the example would be taking the chlorine molecule and breaking it apart into the 2 chlorines that make it up. So in Lewis structure form, which I think is, the more important thing, it's looking at breaking, in this case it would be a single bond between those 2 chlorine atoms and turning it into just 2 chlorine atoms. Now, as previously discussed in our thermochem discussion, bond enthalpies are always positive because energy is always required to break any bond that we have, no matter who we're talking about in terms of which atoms are together. It's always going to require energy to break the bond. Opposite of that, energy is always released when a bond is formed. So when we have bond formation, we'll have energy being released, but when we go to break a bond, we always have to put energy in for that process to happen. And then, of course, the larger the bond enthalpy, the stronger the bond. And I think that makes sense if you step back and think about it. If bond enthalpy is the energy to break the bond, then the more energy you need to break it, then the stronger that bond was to begin with. So now we know a couple things, and this table should be familiar to you because you have this somewhere. Looking at this table, we can see that, generally speaking, our biggest bond enthalpies are down here. Okay, and that's because they're triple and double bonds, and so they are stronger, and we know that. That was prior knowledge. We knew that double and triple bonds are stronger than single bonds, and so we would expect it to take more energy to break a double bond, say, than a single bond, and it would take more energy to break a triple bond than to break a double. And so that's evidence by this chart that we've seen before. So now that we know Lewis structures, we can kind of apply our fourth way to find delta H in a different perspective, only because now we know how to draw the Lewis structure and how to figure it out. So, of course, the fourth way to find delta H that we learned was this formula of taking the sum of all of the bonds broken and subtracting that from all of the bonds that were formed. And we made a list and we did our math. So the difference now is that we're given a reaction, but just you have to be really careful, because just looking at this, you can't always tell what bonds you broke and what bonds you formed. So now we're taking it one step further into you needing to draw Lewis structures, then to decide what bonds were broken and formed, and then to perform the calculation. So like I said, this is not old. It's just that now we're incorporating our knowledge of Lewis structures. And these are easy Lewis structures, so I'm drawing them quickly. Okay. So there we go. There's my decomposition of H2O into hydrogen and oxygen gases, but in Lewis structure form. And so now we can think about what bonds do we break and what bonds did we form. So in terms of what did we break here, let me change my pen color. Oops. So we definitely broke a hydrogen oxygen and another hydrogen oxygen. So we broke 2 OH single bonds. That's it. And then what did we form? Well, we formed an HH bond, and we formed half which is kind of funny, of an O double bond. And so now we can use our formula, broken minus formed, and our chart to do this. So delta H is going to equal bonds broken is going to be 2 times the OH single bond. Where are you? Right there. 463. Oops. I didn't mean to. Oh, goodness. Okay. I can't write on that because it's a picture. So that's my bonds broken. That's it. And then we're going to subtract from that my bonds that were formed. So a hydrogen-hydrogen bond. Let's see, where are we? 436 plus half of an O double bond, 495. Okay, so, and there we have, or we should have, enough information to solve this problem. So if we do the math, I've already done the math. I got 242.5 kilojoules. Notice it's positive, right? And which means it's endothermic. So there you go. We have a second example, which is a second reaction into H4 decomposing to H2. So again, I need to draw my Lewis structures before I can do anything. Oops. So nitrogens. My hydrogens are all going to hook to my nitrogens. They'll bring me an electron, and I think the structure works itself out. Yeah. N2, if you're not familiar with, is a triple bond. And then plus 2. Okay. So again, broken, formed. So what did we break? Well, we broke, let's see. Broke 4 NH bonds, and we broke up nitrogen single bond, and then we formed a triple bond between the nitrogens, and we formed 2 hydrogen single bonds. So broken minus formed. So 4 NH bonds, 391, plus 1 nitrogen single bond, 163. Subtract from that in triple bond, 941, plus 2 hydrogen single bonds. I almost remember that. 436. And as long as I do my math correctly, I should come up with the number. I got negative 86 kilojoules. So in this case, it's exo. So the idea here is not new. Like I said, we've already seen this. We've seen the how to find delta H this fourth way with broken minus formed, but incorporating the Lewis structures just takes it up one notch, so to speak, because not only do you have to be able to discuss what bonds were broken and what were formed, but you have to be able to draw the Lewis structure and then thus, decide what bonds were broken and formed. So that is covered in this chapter. There's also problems in your problem set that deal with this, and so I wanted to do a quick